It's another brief moment in time. We get to see the change on the timelines. We're shifting, twisted bits of technology, lifting up the little bits of reality. While the dream trips through the space-time, we're surely a randomly sparking the photons around me. Let the light flow from the heat show when the photons ignite, highlighting yo. Then you'll know it's that time when we force a change in our mind's eye. Ho ho! A little bit Linux with something in us. It's almost like we something else, autonomous, or maybe perhaps it's that missing piece you need. Perhaps it's that simple message you're searching. Perhaps it's just a different time framing. Us people, that's the fake show in the mainframe. Getting excited, so are the photons. Don't laminate so we can change the coupon. Let me raise the hash rate, submit the coupon, fake it, replace the rate with our major bags. Crypto technology, like cryptographic money and hashing your life into a set of QRs. It doesn't matter, cause this was 3D change perspectives. Welcome to the show. Welcome to the show. Welcome to the show.
What up, everybody? What up, everybody? It is me, 3D, and I just want to say welcome to the show. You're seeing the title, you're seeing it up and everywhere we're going, and that is exactly what we're talking about today. Is all about the algorithms of AI. Now, if you were paying attention, we were having a little mini series. I think I've repeated myself a few times on this, but I'm going to do it again. But it is near the end of the edge of this AI mini series, and I said this is one of the things I wanted to ensure we got in, and so here it is. We're going to go over the different AI topics to catch up on everyone, as well as then go over the actual contextual differences to understanding how these actual AI algorithms work in context. And okay, so how they actually in context work in comparison, because only a couple of these AI algorithms we're going to go over actually even work similar to each other, and that's kind of a somewhat important factor. Now, you guys hear something coming up, just give me a quick second. I am context work. Yep. So okay, my bad. So basically I have some chats up on Twitter and on YouTube. So if you're on Twitter or X, or you're on YouTube and you want to say hello, you should be able to in the chat. Sometimes on Twitter you got to be on the full screen, but they won't appear on our screen anymore, but they will still be. I can react and say hello and talk back to you guys. Alright, so I do want to point out one last thing. We are basically doing a literal of the figurative, comparing apples to oranges. So they're both roundish, sure, but only they do basically the same task, which is give you H2O, energy, and be food or edible. Alright, so I want to go ahead and say thank you to the network sponsors. I want to thank The Organized for teaming up with Bitcoin Live Digital Broadcasting DB, because Bitcoin Live DB and The Organized is a powerhouse combo. I see new heights for both organizations. Now, if you haven't checked out The Organized, they are basically like an early morning broadcast, and I think they're also doing like a later evening broadcast for U.S. citizens about stacks and other general topics. And they're popping off every day, and so it's a good daily thing to be able to catch up on, watch, and see what's new with the digital stuff. So find them on Twitter and all your favorite social media platforms. So we have yeah, there it is. I want to thank Shieldfolio for sponsoring today's episode from within the Quantum Bit, as well as the Bitcoin Live DB Network. Now, if you haven't seen a Shieldfolio, they're like a little black book that are made from stone. They are fade resistant, tear resistant, and even water resistant paper. So you know the info and secrets you store in your Shieldfolio will last and survive whatever you throw at it. I personally have a Shieldfolio, and I use it for my website info, contacts, crypto keys, among other things. They're like little black books. They're pocket sized and ready to be by your side, regardless of your adventure in real life or online. Now, you see right over here, we got a little QR. Now, throughout the whole episode, there's a QR on the bottom of the screen. You can scan that whenever you want to go to shieldfolio.com today. But if you use that code BitcoinLive20, you actually get 20% off your order when you go to their website through the QR. I think it's just like the Shieldfolio main website. Now, you can buy these at like Walmart and a bunch of other places, which is really awesome. And I personally think they're just dandy, so to speak. Now we're going to go ahead and jump into jump-ins before we continue on. Wait a minute. What? I know you guys can hear me. I know. I accidentally turned it on when we had the other thing on. And now it is not correct. I might not be. Alright. Let's see. We might just have to do this in real time. What happened here? What the heck? That is not correct. Yep. I'm just gonna have to. There we go. There we go. Let me get this set up for you. I apologize for this confusion. Sorry. Alright, everybody. Okay, it turns out like my lock got unlocked somehow. And I just want to thank again Shieldfolio for sponsoring today's episode. Because we are in the photo of the quantum, or the greater fourth quantum dimension. Blah, blah, blah. Having fun with it, yes. But basically, we're here to do more than we normally would be here for. Because we're here about AI. Alright, so to get stuff going. Doesn't matter when you're watching this. If you're watching this right now, later on, or in the future, you can, at any point in time, just basically scan one of these little QRs that's about to pop up on your screen. You should be able to scan that little QR right over there. Be able to scan it, and it will take you to whatever site we're on. Like, for example, right here, this is the Deorganized Media YouTube channel. We were talking about them just a few minutes ago, and just wanted to point out that Deorganized Media, they do go live almost every morning and every evening, so check them out for your daily hookup on what's digitally popping. So we're going to kind of play catch up a little bit here as we start to move on. Okay, that looks worse than I thought it was going to look. Don't matter. These are videos we're not going to actually watch. Alright, so anyways, in this episode that you have on the screen, this was our first episode of the AI miniseries, and if we kind of zoom in, you can kind of see what we're actually talking about there. AI agents, and this is where we found out that a lot of AI agents are just AIs, but people can also be agents of AI as well, which is kind of misleading in the situation of how everyone talks about them. So no one ever really talks about how you may be one of the agents of AI. So in the second episode, which we have on the screen in front of us now, boom, there's QR. This one we got caught up on a lot of the major AIs, DeepSeek, OpenAI, things like that. But we also like pointed out problems with the AIs. Like, for example, this one was from DeepSeek, where they actually can even obtain any information, including all your keystrokes, including if you're using it 100% offline. Like, doesn't matter. They have access to that information somehow through other services and media, whatnot, all sorts of different ways. And it gets really creepy. But we also then eventually highlighted potentially false or at least open AIs before we actually concluded on one real false AI. So it was a really great episode. Then in this episode of the mini-series, this was the third episode right here, we went over actual in-use cases of AI. For example, the intro. Before we looked over a handful of actual no-install, ready-to-use over-the-web AIs that do practical work. Like, again, the intro was done using a no-install, web-ready, practical AI that just generates music based off of lyrics you give it and a description of the song. So I believe this was pretty much the most recent episode, and we went over the AIs that we're about to talk to today. We went over a bunch of different, specifically the internal algorithms of AIs, and that's where we're taking off today. We are going to continue on that conversation. We're now going to compare some of these AI algorithms today. So if you watched that episode and you still feel unanswered, we're answering them today. Now, if you watch today's episode and you feel left out, well, go watch this episode because it's going to fill in any gaps that you might be missing out on. Ooh, all right. So how do all these different algorithms get to the same answer? That is the question. That is the question. So what we've been doing is we've been doing a free search query. Today's free pre-search query for today's episode is AI algorithm explanations. I didn't use any of the stuff that you can find in here, and if that means if there's actual information in here and you can find it in today's episode, then they just happen to cross over correlate, which is cool, right? So if you want to learn more about how these algorithms really actually do work, come down here. You're gonna find more information from pre-search right here. There's tons of pages. This is the first page. Tons of pages. All right. So we're going into, well, what seems strange, but I've done this before. I've used GitHub before to get stuff on the screen for you guys. That way you guys can like have a link to go look at it later on or whatever, instead of it just being only in the video. Well, I went a little bit further and took an extra step and made an entire repo replacing those images and stuff like that. I'm gonna I know we already have links to stuff. I don't plan on removing those. I'm just gonna try to figure out a way to merge that data into here and to be able to have multiple links to that same data point or whatever, but have a centralized location for you guys to start accessing stuff that has been displayed or made for the show, because we have made bits of code and things like that for the show. So maybe you guys might want to play with that stuff. We're going to make sure you guys can from now on, is what we're saying. So here's the link for that, as it will be growing soon. So if we go to today's episodes folder, we have a whole folder for this little mini series, believe it or not. So we can see here we got some pictures in for today. We also have the AI agents dice from a few episodes ago is already in here. So I've already started working on the process of getting the data where it needs to be. So if you're looking at the screen and you're wondering, did I break it? No, I didn't break it. But if you don't like it, comment you don't like it. Dead serious. If you do like it, like, subscribe, share, maybe comment what you do like about it. I do have a reason for doing it for today's episode. One of the reasons is the fact that I think that it does make some of the words easier to read and allows, when I say specific words, this word or that word, makes it easier for your eyes to direct what we're talking about. But it also makes like more of the background, like the background of the website. Sometimes you have ads and other things. Some of that's gonna be able to blend more into the background of our moving background. But if it ends up just being a flop, let me know, bro, and after today's episode we can always drop back. I'm just trying new things. Alright, so it says we are returning to the show. Alright then, here we go. The actual bit you guys are here for. I know this is what you guys wanted to know the most. Like, what is it? How are we doing this? is we're comparing algorithms that don't really have anything to do with each other in a lot of aspects. They work differently, but they all get to the same point, right? We're going to ask these very 6 basic questions. It's actually 5, but I had to put in strong workflow to help a lot of this stuff work out, and we'll explain that later. More about that later, or whatever. But these are the basic questions we want to answer. These questions should help us actually explain how these algorithms work in similar. So the way I want to show how they're different is by showing how they work the same. Because when you see how little some of these actually work the same, it will probably blow your mind on how different they really are. And then you'll see how some are just not that different. And then that probably won't be mind-blowing, but I mean, like, some of the stuff that's in here I was not even expecting, which I really like about doing some of these. This is like, I think, the 5th or 6th episode where going into it, I kind of knew what was up, but after doing more research and looking further into things, I was able to, like, either change my own perspective because it's like I wasn't completely correct, or, you know, it's like something I wasn't expecting popped up that maybe didn't change my perspective, but it's like, whoa, did not expect to see that. And this is definitely one of those episodes. So what we have, if you look right here, I keep looking the wrong way. Does this define anything? So does this algorithm have the ability to make a definition of something? I know to some people that might be redefined or defined and redefined, but we can just put it simply. Does it have the capability of defining stuff? Yes or no? It should be as simple as that. As soon as you try to put anything else to it, is it already defined? If it needs to already be defined, it is not defining. If it's able to redefine, it is defining. So if it needs to be defined and it redefines, it's doing both, which means it is definitely defining. And that's the other thing. A lot of these will have points where you could say, yeah, some of these AIs, maybe sometimes, and then maybe how you set it up, maybe not. So there's tons of times I'm looking at the overall highest average. Whichever one averaged out to be the one with the more average. Sometimes these cut down quite to the line. And so we looked at the number of times as well these sparked in difference, so we could get a number of highest point. And when they even out, we don't consider any of those. Instead of putting the both in, we put none in. Alright, so now you know how some of this came to be. Continues. Does this algorithm have the ability to act? A lot of people are going to think this is, I honestly think this is probably the simplest one of them all. Does it have the ability to perform an action? So in the previous episode, we talked a lot about a sorting algorithm. A lot of these sorting algorithms, a lot of this just sort stuff. So that's not the same as acting. So sorting stuff is like adjusting a database, setting stuff into arrays, not acting. Acting is performing something normally like a human, but it doesn't have to be like a human. It's just like outside of its own database, outside of its own self. But if it was its own code, that would be acting. Like changing its own code would be considered action. Changing what's available in the state memory, not an action. Sorting and adjusting its databases, not an action. Going on to X Twitter and posting about this and asking Grok about today's episode, definitely an action. So, now, next question. Does this algorithm sort stuff? This is, again, like its internal stuff. It's going to be database, labels, anything. Anything to do with its internal workings besides its code. And it's sorted. And it determine the difference between A and B is not the same as sorting. Sorting is literally just putting something from an open-end array, from like one big array into different multiple arrays or something like that. Or moving stuff from one database spot to another database spot, or from one K cluster to another K cluster, or adjusting how the labels are set up in a specific order, because maybe that is a way it determines something, but so it has the ability to sort the order. Those are sort. Okay. Does this determine? Now this is more like what people think of sort. Can it tell the difference between A and B? Can it tell the difference between two things? Now we're not asking if it doesn't really, like, it does not matter if these are like items or not like items. It has nothing to do with that. All this really matters is, can it look at object A and go through some protocol to make a determination of object A? And if there's two object A's, regardless if they're the same or not, that does not matter. Can it make determinations of each and between each? Those are all determinations. Now those are different types of determinations, like between each and of all each, are all different determinations. Are they ever blanks equal? So for example, I was saying object A. So are they ever object A's equal? Now this is where it actually matters. This is all it really matters. If the two objects are not equal, so it's like obviously different in some retrospect that a human would go through, that's not equal, bro, then we don't care. Like, it doesn't matter. Like, that determination and sorting, or defining and sorting, or sorting and acting, would be able to figure that out on its own. So we only care if they're ever equal. If there's ever a possibility that object A can, both object A's or all object A's could be equal in some way, shape, or form. And when I mean that, like in an obvious to most people, then this is when it matters. Because that's when it needs a protocol to make additional steps of actions, determinations, sorts, or whatever else it can do. It has to do some more of it at this point. And so at this point, that's a really important fact that I haven't said yet, that I've been holding. Define, act, sort, determine, equal. In that order is super important, because define is the simplest. Act is even a little bit more difficult. Sort is a little bit more difficult. Determine a little bit more difficult. If they're two equal possibles, a little bit more difficult. So they're in place in order from easy, top left, most difficult, bottom right. In processing, not always in doing. For example, most people would probably say that defining and determining are probably the two easier ones on here, like logical sense for processing, logical sense, like how does the computer actually logically process that data or whatever, not the actual like processing speed or processing power, processing take it, how much power, energy it takes to process that data in a length of time. Okay, those are two different things. So the order set is based on processing electrical input plus time, or multiplied by time, to get output, and if output is how close the output is correct. So those are the determiners of top left is easy, bottom right is hard. So the last one, very bottom one, says strong workflow. This was an add-on, so that way the next thing I'm about to show you will make more sense. And this is the eggs and potatoes, or the meat and potatoes of this entire thing. This is what your eggs and toast is for, bro. What I'm about to show you is what today's episode really is all about. It's going to be a mouthful, but at the same time, we're going to have fun with this, because let's just get into it. You know what? I think with nothing moving on my screen, it is very distracting to have that stuff moving in the background. I had this set up to where I could just easily turn that off Glad I did. Alright, so basically we're going to ask the 5 questions. Or the 6. Alright. I want to give you a couple informational points. Stuff all the way closest to my face. That stuff. Those are the AIs. These are the questions. Now, you'll see green check mark boxes and X's. Pretty simple. Green check mark box at most average with the most number of times is yes. X, no. And then we got some stuff to add in to ensure that I don't forget for each one of these. So when we're going through here, you're going to see these green check mark boxes have alignment orders and number of. So it is aligned and ordered where the topmost has the least number of green check mark boxes. The bottommost has the most. But also we are considering processing power in the strong workflow. So the most bottom one takes the most processing power to do out of all of them, regardless. So the lower bottom they are, the more processing power it should take compared to any one above it that have a green check mark box for the strong workflow column. All the ones without the strong workflow column are not considered in that manner, but should be loosely set up in that manner. So if we start seeing stuff in similar columns, which we'll explain a bit more in a minute, then we can determine that those might be used in other systems. So starting off with cluster, it is a very basic way to sort stuff. Now I'm not saying if something sorts it uses cluster, but there's a high chance that it does. Because it's a single checkmark box thing. It's the easiest thing to do on this list. I mean, there are actually easier ones than this, but I mean, like, for what we're talking about, this is easy. And you can actually set an array instead of actually using a graph. So there's a lot of AIs that use graph or array as graph to sort insanely fast with this cluster algorithm. And that is the sweet spot of this algorithm that makes it usable even on, like, I'm pretty sure you can get this working on a flipper. Pretty sure you can get the most basic cluster algorithm to give you an array as grid output on a flipper, which then you could use the flipper program or whatever to actually turn that array into a real grid on there on the flipper to see some amount of data that might not be, you know, like what we're seeing in front of us. So you can turn like a CSV into a be able to sort stuff by like things like that you've seen the most or something like that, some kind of predetermined set. All right. Now for the rest of this, we're gonna go completely off the script. I have a huge script here. We're just gonna read the script from this point on. So this is the questions we're using to answer these easy 6. These are the answers for the 6 easy questions. We'll be zooming in. Oh, let me switch back over. I'm gonna be going back and forth. So I apologize if I keep saying things and saying we gotta move back over. All right. So this is what we're using. I'm gonna get you the QR before we move anymore, because now, boom, you can have a copy pasta right in your lap if you scan that QR. All right. So reading this chart is pretty simple. Kind of explain that. Something to consider, we only need to ask the first 5 questions. Again, that 6th one is just for setting stuff up nice and neat. Alright, now I do want to point out one other thing. This graph is, again, ordered in that one way. So if we see any single group of like 1 green boxes, for example, the cluster, or for example, groups of 2, there's 2 green box groups and that have exactly 2 algorithms in it. And in the 3 green box group, there's total 4. But when you keep going down, you actually end up finding a couple of more algorithms that only have 2. You end up with a whole total of 2 green box being like 4 or 6 or something like that. And so the largest ones that we have is 4 green box with a total of 7, and 5 green box. And then no, it's 4 green box and then 2 green box, because 5 green box has 2 and 6 green box also has 2. So yeah, 6 and 7. So 4 green box has 7, 2 green box has 2. So those are like, every one of those green box groups are special sets, meaning like anything within that group should have some kind of similarity to it. Let me just read the script. If you were to go and ask Grok right now about this episode after today's episode, it would probably be easy to tell you that the 4 green boxes and the 2 green boxes share similarities to at least their grouping and indirect neighbors. This is to mimic how clay clusters work, which is a common self-labeling method used in memory controlling labeling or learning algorithms or deep learning algorithms. So each green box total group is similar in some manner, while also any neighboring one directly around it is also in some manner similar, even if it's not in the same green box group. So this gives us a lot of information very easily. So we can take all these different things and very simply understand more. So for example, you could say cluster is closer to hierarchy than cluster is to gradient descent in similarities, even though they're not anywhere near similar to each other. They don't do the same stuff. Point seen. So yes, this image mimics how many of these basic AIs are going to work, because one of the ways that a transformer works, cutting a bunch of heads off of hydras, and neural networks does something similar. And with this method that we have it set up, we can cut off hydra heads easier with this setup, because it's going to kind of show you with your eyes that there's someone actually have to say it. Alright, so cluster doesn't define, it cannot act, it only sorts. It's a simple sorting algorithm, perfect for verifying other sorting algorithms to catch outliers and edge cases. The simplicity of the algorithm should be obvious. It has only 1 green checkbox in an entire row, and is centered to be on that. Like its green checkbox is dead center. That was done on purpose. See why? The top left is simply it's simple, and the stuff more work intensive again bottom right. So even in this list that we have set up, left is less work intensive, right is more work intensive. Top is less work intensive, bottom is more work intensive. Alright. So going over to see the notes, it says clusters are great for capturing data for review. Nice. And it's like you use a cluster to take the data and figure out where you need to review the data, what part of the data you need to review. So hierarchy is really just a defining way to access and take clusters of deep memory. But it can also be used for APIs, determiners, and other simple tasking that needs to act after comparing 2 or more objects to each other. Well, it can act, and it can determine if 2 things are ever equal. Because again, like I said, if it can determine if 2 things are ever equal, then it can automatically determine if they're not equal. Like it automatic. The only other way it's not automatic is the other way around. Alright. So it also does this, and it can normally do this in a non-deterministic way. That's kind of important. I don't know why, but that's kind of important. Actually, I do know why. Non-deterministic way means like it's not determining anything. Hey. So oftentimes hierarchical AIs use interpreters to form this hierarchy, and often for public guardrails. But when used properly, it can actually be an efficiency booster for most pre-AGIs moving towards the actual AGI AIs. And we do have notes here. Hierarchy is for forming the flow of data usage from different systems working together. And if you see some of these have this NSAS, that's a not standalone solution, meaning if it has NSAS, it needs other things to be considered an AI or a solution for AI usage. And if we're using this hierarchy one, for example, if we look, it has act and if equal. So those 2 points, if we have other ones that have specifically those 2 points and they do not determine, there's a chance, a very high chance, they actually use hierarchy determinations. Now, if it doesn't define and it doesn't determine, it does act, and it can do if it is equal or not, we can almost guarantee it's using hierarchy determinations. Alright, so gradient descent. Gradient descent is a really neat way to allow AI to see a different output. Or at least a different output perspective. It does both. Yeah, okay. It says a different output and perspective of output simultaneously. But the maths is really just based on like the least amount of tension and friction based upon a multiple dimension field or graph. So oftentimes this is used in conjunction with probability data to see which of the outcomes most likely have the least resistance or have the most probable answer, or might be the most probable for the answer. So gradient descent, it determines, and it has the ability to determine if 2 things are equal. Perfect. It's a different way to determine things. Now that's a good point. So that means gradient descent and hierarchy are both ways of determining things. Hierarchy is a non-deterministic way, and gradient descent is a deterministic way. Awesome. Now we see how those 2 things side by side have likeness to it. They also both only have 2 boxes. Holy crap. They both have the same likeness. Well, that just shows that the amount of likeness they have between each other, even though are different, it is similar because they're right beside each other. Now, we probably could arrange formal ontology. Like you could say there's some wiggle room there, but we'd have to give gradient descent a 3rd checkbox, which formal ontology, I think there's a lot of people that would go, it doesn't do one of these 3, right? It either doesn't define or it doesn't sort. But I found that no matter how many times I looked up different ways people are using formal ontology in practical use, they seem to use a combination of the 2 to check itself. So I used both in this point. I wanted to bring that up because, I mean, there's a lot of stuff that you could easily go, nah, bro, that ain't right. But I am trying to put this stuff in a point to help you understand the perspective of how this stuff is similar, even though it's not. They don't do stuff the same way. So, Bayesian, or the Bayes network, or the Bayesian. So here we can see the Bayes network is in some similar to the formal ontology, but instead of defining, it determines rather sorting of objects that may or may not be equal in some manner or another. So like, for example, if we come up here, formal ontology determines directly, while gradient descent, formal ontology defines and sorts to determine, while gradient descent determines directly. I said that backwards, my bad, guys. So it's just another way to make determinations. And again, they can also determine if things are like or equal. So again, formal ontology may have been used to preset the possible labels, but it isn't used on the fly. And often labels have to be predetermined. So already we're seeing that some of these have, like, some of these last 2 algorithms have similar but different vibes, right? They don't kind of vibe together, but they do at least are able to work with each other. And on all of these, they can work with each other if you work top down. You don't want to try to grab like supervised learning and decision tree learning. Nah, you might need some of that stuff in the middle with those to work properly together. So we're going to go down to decision tree learning. Decision tree learning has a few more marks in its boxes. Oh wait, hold on. I forgot. So formal ontology is great at defining data for labels. Bias nets help determine possible correct answers and sometimes determine potential outcomes. It's actually, the Bayes networks was like the first ones where people were like, oh, AI can predict the future. Yep, that was that one. So decision tree learning. Okay. Decision tree learning has some strange connection with the last two algorithms. It contains formal ontology boxes. It does. And it is basically an extension of formal ontology algorithm. Now keep in mind, I do mean that in a figurative retrospective perspective. It is an extension. You could make a decision tree learning algorithm by starting with a formal ontology algorithm. But it's not actually needed to do that. You can get there without it. So there is a lot of, originally decision tree learning came from formal ontology. It was originally an extension. So I'm going to continue calling it an extension. Now, the important part of decision tree learning is in the fact that it can do actions. It can act. Many people don't realize that decision tree learning can be set up to act upon landing in spots on the decision tree downline. So the tree downline, or the forest cluster group sideline thing. Like how you say, I call it the tree downline. I don't know what you guys call it. Some people, I've seen some people call it a forest cluster point or sideline downline, or I don't know. So this tree learning is often considered a low-level AI because it can sort, define, and have equal or not equal objects, and it can act. This is known as what I call a pre-programmed intelligence because it is, in short, the easiest example of exactly that phrase, pre-programmed intelligence. And you see, there's not much missing, but it says tree learning is light if coded well, but sometimes considered low AI as a standalone solution. It's the first time we're really coming across something that is what most people would feel is standalone, but bias network actually is standalone because of the prediction ability. Not really prediction ability, that's randomness multiplied by probability, what that is. So, large language models, again, LLMs. They are similar to formal ontology. Bring that back down. Can you still get off screen? But more often than less, LLMs tend to be more work intensive. Rather, it's a pre-built workload or on-the-fly workload. LLMs require tons of time and effort just to get doing the simple task it does. Define while sorting like or unlike objects. That's all it does. Define while sorting like or unlike objects. Just like formal ontology, but in a different way. So we see how LLMs, although they're very similar to formal ontology, they do handle the similar task completely differently normally. Normally they're differently. So they are nowhere near each other on this graph, or this chart, or table, whatever you want to call it. I don't care. Alright, so now we're going to look at what we got for language law. LLMs handle data in ways as similar NSAS AI algorithms, but often are intensive work and more accurate. That's actually what the intensive workload gets you. More accuracy. Deep learning. It may be difficult to see how deep learning uses hierarchy internally, but this graph does show, because deep learning contains the hierarchy combo green boxes. We're going to go back up. Hierarchy green art. Deep learning has both of those boxes. Now it does have one of the ones that said it shouldn't have, but deep learning uses hierarchy internally. Like, it's one of the things that makes deep learning even possible to be used in most eyes. Without it, it's absolutely just random picking. Basically all it does. It uses hierarchy to get rid of the randomness out of its pick order. So we can see deep learning has these abilities to determine before, while, or after it acts. And often deep learning is the favored form of AI training methods because it self-acts, can even be self-guided or outside-ly guided. It can be guide route. This is often where AI daydreaming actually comes from. When AI is being guided hard, but still has full deep learning control on its own. Like it's got a lot of guardrails, but its full deep learning ability is turned on. So it's randomly picking crap. That's where AI daydreaming actually came from. And to this day, that's the easiest way to get AI daydreaming is you set up a basic art model or art re-rendering model, and you just do not lock up its deep learning. You take out the hierarchy, and that's pretty much it. I mean, like, there's other ways to do it, but that's the easiest way. So, supervised learnings. Oh wait, hold on, wait, we got stuff. Deep learning. Deep learning is great at picking between different possibilities, and when weighted, tends to be accurate. I keep wanting to highlight these, I forget I can't highlight. So, deep learning is great at picking between different possibilities, and when weighted, tends to be more accurate. Supervised learning. Many people use deep learning in conjunction with supervised learning. It's obviously why, I think, there's one green box mixing between the two. To have them working together, there's one green box missing. So this algo can sort equal and non-equal objects. It can act at some point in its loop order. Often the act is around the same form of user interaction. So I said that wrong. Often the act is around some form of user interaction with the algorithm. So basically it doesn't act on its own directly. It needs something to tell it that it's allowed to act in some way, and a user interacting with it is definitely a way to do that. So supervised learning can perform more work in comparison to other SAS AI algorithms, or the ones above this on the list so far, but it almost always needs a user. I mean, it's designed to be need a user, so it needs a user. Excuse me, I'm drinking some coffee. I got a coffee cup on my stand. You guys see it? I'm drinking some coffee. All right, unsupervised learning. So unsupervised learning often has a raw deep learning system internally, but it can be easily without that raw deep learning system. So a few run these alone. So very few unsupervised learnings run without raw deep learning, or without deep learning at all, as a side coach. So it's even ideal to have a supervised method watch over an unsupervised method to get a more full range of control, even on the fly or an active generation process. So there's tons of times where you take a you take ChatGPT and ChatGPT for all, and you use ChatGPT to control GPT for all, to get it to produce stuff to where you're like, oh, I want it to produce cartoon character with a real human body, whatever, and you produce a real human, and then you have it relayer on top. You just stop it partway through and you have it redo cartoon character, then have it mixed together, and you get more control. And then you can have in a faster amount of input or a faster amount of outputs, or less number of outputs, you can get really what you're looking for, or more exact results overall. So next we'll unsupervised learning. What do we got? Unsupervised learning does, thinks, and learns just as supervised learning and deep learning, but without a user. Now it's kind of important. Deep learning at some point almost always needs a user or AI to interact with it. It needs another algorithm or a user to interact with it. And that's weird, but it's only got so much work to do until you give it unlimited data, and then it just never stops. Transform. Notice something strange about transform? It is a deep learning method, but just not the same way. So again, they're nowhere near each other. They're nowhere near each other. Deep learning way out there, way far away from each other. So this also means that the supervised and unsupervised learning could be in part workable with transformer algorithms, like they can be used with deep learning algorithms. This is kind of like just opposite ends of the spectrum. So this is why they obviously similar algorithms are separated by these two very specific algorithms. That's why supervised and unsupervised are specifically between deep learning and transformer. The transformer says handles outcome workflows and the actual work, but doesn't normally control labeling. Means it can, but it doesn't normally. Artificial neural networks. Artificial networks are great at determining while sorting in a manner that is normally to downsize the end output or result. We can see how these networks do work similar to a transformer, but with differences. Nowadays, artificial neural networks can be very efficient on the workload, but still does a ton of microprocessing, micro-looping, and trailing variables. So also neural networks normally require either more time ahead of time to prepare a lot of stuff, or more time in general to just get done. Even though neural networks can be designed to be way more light and dynamic compared to transformers, the more common average is that they actually require more work to get the most real tasks done with real AI systems compared to the same real AI systems just using transform. I actually can't believe I had to perform that test. Although, like, at first when I was doing the test of like finding AIs where you could just like swap out back-end and internal systems to find out like different ways to do things and how they actually differ in different reactions and stuff, was really fun at first. And then I discovered how much more variables there really are in these. You get to a point where you need like years and years to just sort these differences when it comes down to the actual internals at the cores of the internals. And I mean that down to like the nit and gritty, well, maybe the cores, maybe the pores, nit and gritty pores. Okay. So what do we got for artificial networks? Artificial networks handle simulated considerations and prediction style modelings. I'm going to say that one time. Artificial neural networks handle simulated considerations and prediction style modeling. Nice. Reinforcement learning. I'm really giving an opinion for a second. So I think reinforcement learning is how the people at Google actually figured out what they needed to make transformer models actually happen. So much better than what they were before, at least. I think this is because they were doing AI reinforcement learning, like the reCAPTCHAs or whatever, right? I should say the AI reinforcement human verification thing, right? So defining objects in a picture based on it, and it contains something resemblance to the reference, right? But yeah, you click the box, verify it, it's definitely a reCAPTCHA. We all did this for like 2 decades, or a lot of people did this for decades. And that is where the data showed other people were abusing the token model by resubmitting old good tokens. So it was a token that was considered good, and it was being resubmitted as if it was brand new. Even though they were out of sync and all that, it was just bypassing all the checkboxes. It was basically fake verifying. And the data actually eventually showed it, that it was happening, and that you didn't click anything, but you got to the same goal. And by submitting a previous good token, you had a 1 in 9 chance to be correct, because your token was just what box you clicked, or what boxes you clicked. But in the end, it was actually only 1 of 3 boxes recorded in that token, because the token records 3 boxes. And you only need one of those boxes to be correct by submitting that token. There's some room of error. And then you can actually, it will go basically try again. And you can do that 3 times and just completely bypass the system. So you would just submit the same token 3 times and bypass the system. Because it takes into account where if you were just fucking up a lot, you would submit a partially bad token. And so you had 3 chances, and all your good chances stacked. So as long as you got 1 good per, you could get it in each and every time. So over time, this stuff showed out. I even had a website that abused this trick for a long time. I used to tell people all the time, just go log into this website and use it to collect your faucets. We used to call it 3dbtlist.com. It's not controlled by me anymore. It hasn't been controlled by me since like 2019. But it used to be to go there and use it to go to faucet sites, and it would bite after using my site 2 weeks ago. All your faucet sites, you would get a web worker in the back of your browser, whatever browser you're using it in, and after about 2 weeks, it'd get in sync and everything, and it would resubmit. It would just save. It would just hold your last good recapture verification token. Just hold on to it, and the next time a verification token API string or certain thing popped on your screen into your view, it would just submit this token instead, and it would hold on to that token until it didn't work, and then you would do it again. And so I think they used this data to, because there was a lot of places using this trick to get bots around it and to get users around it to get it out of their website. They could put in that you had recapture, but it never show up. And so looking at human verification data, edge cases would actually show this trick the quickest. And to get that trick to show is actually the method of transformer. You multiply it out by like 1,000, and then those really tiny changes become a lot more drastically easy to see. You pick out the very topmost, reduce the stuff back down to find the real data points, and boom, that's actually how transformer works. So my personal rant, let's get back to what it says. You should be able to see that the reinforcement learning is basically transformers just with more steps. And it makes more sense to say transformers are a more efficient enforced learning methodology. Simple as that. So reinforcement learning slows the system down but allows for a more stronger on-target positive curve. So it tends to be correct way more often, especially over time, compared to other ones. And that is, again, for on target, for whatever the target is to be. And it has to be very specific, while a transformer doesn't need a specific on target. It needs just a target. And if you don't know the difference between on target and target, a target's a general amount. Like, I have I hate to use military terms with you guys, but where I know the terms from, I have a missile, I shoot it, it has a 5 kilometer blast radius. That's my target radius, but it actually only hits on target within the about what was the ones I was doing? About its radius double. So it has a nose radius. If the nose radius is 3 inches, it's double the nose radius on each side. So of course, I'm not gonna do the math for it. It's like 9, okay? Anyways. So on target is the actual bit it is specifically hitting. Target is the range it could damage. And when we're talking about stuff like this, same thing. On target is very specific, while target is very generic. Alright. Yeah. Evolutionary algorithm. I almost read the same thing twice. My bad. I don't think there is really much we can compare with evolutionary algos because they are so different. So I try to strip the category down to the most common ways that we actually see these algos being used. And when you look into evolutionary algos, we can see that they take advantage of multiple different algorithms that are higher up on this list. You could almost mix and match a few of these higher algorithms in this list, right, and still end up with this with an evolutionary algorithm. I think this is probably true for also reinforcement learning. You can mix and match to build up one of multiple algos that actually could be considered reinforcement learning from higher up on the list from reinforcement learning. So the same will be said about many of the algorithms from below this point on the list. So reinforcement and evolution algos, they can sort, they don't normally. Oftentimes they use natural law orders to consider information sorting. That would, let me re-say that. Evolutionary algorithms and reinforcement learning algorithms don't need to sort because they use natural laws to consider information that would normally be considered from sorting or obtained from sorting. Yes. Sorry, it was written wrong on my paper. I had to say it right. Evolutionary algorithms tend to be more complicated algorithms. That's defined in this solution, though. That's right. These are more complicated, but they normally find a new solution to problems that we didn't have solutions for. So they're really important in that aspect. Alright. Hybrid intelligence system. A full-on. That's right. Here is a multiple setup AI system. This will always be a mix and match of different algorithms and AIs, of course, to get results that will seem like AGI or even seem like pre-AGI. These are often the really smart bots that don't quite mimic humans very well. It's always a presentation that's flat. So these take, it's all the way across, all of them, all the boxes. Takes multiple systems and allows full possible options and often seems like AGI. You should actually say it seems like pre-AGI. So AC, Artificial Intelligence Systems Integration, or Integrated. AISI or AC. AC, oh yeah, this is just a different hybrid system. Hybrid intelligence systems are normally completely separated, and something allows these systems to work together, like simply sharing the same database or having an actual program or algorithm or AI handle cross communication. AC, on the other hand, handles it all internally on its own. It's like in a whole package deal. So you pack all the algorithms and AIs into one big old package to handle it all together without having to directly consult anything else other than like internet calls. These are pre-AGIs and often can access computers and internet systems as if they are users. These are often the user simulation methods for handling combination AI systems. So you normally use an AC to handle input, output, and internal communications from hybrid intelligence systems and lone AIs and data sets. So AC is a pre-AGI system methodology to allow what seems like true AI, even though it's not. And that's kind of important because whenever something seems like true AI, meaning it seems like it could change its data, change its internal structures, change its code, rewrite itself, learn from its own mistakes. But in reality, they really don't. They really don't. Because I know learning from your own mistake is not the same as a training model slowly changing to make sure you just don't make old mistakes as often as you did before. Not the same. So that was a lot of talking, a lot less showing than usual. And if you missed out on the last episode, go back and use the QR to check that out, or check out the YouTube description later on down the line. See that link. Basically, we went over these AIs before in that episode, and we really showed how they worked individually, how each one of those worked on their own. So this is a lot on this list. And yeah, this is actually a list of my favorite AI algorithms. But these are also probably the most broad different working AIs, even though much of these work very some of these have very similar methodology, right, to each other. And that's the whole point. The last two episodes of this mini-series is just to help show that even though AIs get to the same results, they do, at the moment, they're different. They're going to one day all get to the same result. But right now, they do work way different. And even though they work different, they are trying to get to the same result. That's the beauty of AIs and algorithms in general. They should be an endless number of possible ways to sort data. And yeah, that's the real perspective today. There was a time when people used to say, sort out your problems. And when we look at AI algorithms, they mostly just sort out data to then define data, to determine from that data, to then make acts to compare. And sometimes one is like chasing the other. It just one causes the other, and to hit that goal and to make it achieved, you just gotta keep going and snowballing until you get there. So if we can learn anything, simply sorting out your problems into simple rows, then adding complications with columns, then average the good versus the bad to determine the most likely possible outcome to pick from. And maybe that might help solve any problem you have in your future. I mean, if it gets AIs many love so much to generate what people call masterpieces without even being true AI, then yeah, simply predetermine or on the fly determining sorting algorithms into multiple dimensions until only one dimension stands left might just be your answer. And think about it. It's not that bad. Really, not that bad.
Yo, did you think you know? Did you think you hold? Did you think something new? That's the goal, to see from a new degree and get the change your mind needs to find something new. Life suddenly is easy for many, but when a wall appears, sometimes up is all you see. So let 3D guide to the side, yo, where there's a door though. Just be careful on your way out, for the first step is a do-si-do. A little bit Linus with something different, it's almost like he's something else. And regardless, maybe, perhaps it was that missing piece you was needing. Maybe it was that simple message you was searching. Definitely it's just in different time for defraying a mental mind state, separating us from our own mental mind tank. Boom goes the blast of thought. Boom goes the last spark with part. Boom goes the mental mind tank. Don't your perspective hit on the way out. Don't let your directive stop you when you doubt. Don't let the dire detection stop you from being getting excited, so the photons are delighted. Don't hesitate so we can line up the hash rate. Let me surmise the tide, submit the rate, and reduce the face while we mine our major bags. Crypto technology like cryptographic money, while hashing your life into a set of QRs. It doesn't matter, cause this was 3D changes perspectives. Thank you for joining the show. Please return next time for a new role of perspective. Thank you for joining the show. Please return next time for a brand new perspective. Of perspective. Thank you for joining the show. Please return next time for a brand new perspective. Thank you for joining the show. Please return next time.